Let me see, I was trying to invent, ideally I would have sent you guys an email with the grades, but I haven't gotten that up and running yet. So I'm going to have to play a little game here. Let's try this. Yikes, that's pretty small, but let's see. All right. Can you guys read that? No. If I turn off the lights, it's going to be dark forever. All right, let me do it a little bit differently. Let me, I'll just, okay. So, that's not a grade. That's a random number between 1 and the number of people in the class. I want to show everyone everyone's grade, but I don't want anyone to know their neighbor's grade. And I think I've got a little technique to do it. So, find your name, okay? And memorize your number. Don't memorize anyone else's number, okay? Does that make sense? Okay, here we go. So everyone got their number? Anyone not got their number? Do I need to go back up? Everyone got their number? Okay? Okay, now I'm going to pull this back over on my side so I make sure I don't screw up and show everyone the wrong thing. Okay. Okay, so now the numbers are listed numerically and the grade is listed. And then I'll talk about the grade after you see them. Oh, please. Oh, come on. There we go. All right. So that's a number out of 100%. Okay. So you have to memorize your number. Remember your grade. And then I'm going to show distribution and explain where A, B, C, D would be. Everyone got it? Okay, can I take this away? All right. Is that too cute by half? Too clever? All right, fine. So this is the distribution of those scores. Now this is pretty skewed. Let me explain what I did. There are a number of zeros in homework, and I will drop one. If you've got a couple of zeros in homework, it's really clobbering your grade right now. Plus, which a few of these people don't really exist. Like I think there's 2 people who've never shown up, but they're in the registrar's list, and I didn't have time to cut them out. So I think the bottom set are just pathological. I suspect a number of people right in here have, I hope, some decent excuse. I believe we're dropping 1 homework grade. That's what I wrote in the syllabus, okay? So, you know, if what this is 2 missing homework grades out of 5, there are 5 homework grades in both exams. Take that into account. On the other hand, if you're in this clump and you've got everything turned in, you're in that clump. So, okay, that's not good. I took a straight average of the 2 of everything. The homework scores are weighted by how big they were. But the 2 exams I just averaged, just boom, boom. And the distributions on the 2 exams were comparable. Okay, so what will I do with this distribution? Clearly, if any score down here is real, it's going to be an F. Okay. Well, let's start at the top end. I mean, A is probably going to be somewhere in here, right? Maybe down here, but I just don't want to promise it. All right. B is probably going to be somewhere like that. Okay. And then C is going to be down here. If the final distribution ended up like this, I would probably spend some sleepless hours. Believe it or not, professors do spot these things. I don't want to give D's. I don't want to say that if you're here, you're clear and free of not getting a D. And certainly if you're there, you're not clear and free of not getting a D. You might get a D. Okay, and if you're below... Oh, it's my laptop went to sleep. And if you're below that, you know, that is an F. So I hope you're not down there right now. Okay? I am going to take into account special, if your test grades, and already there's one case in the course, is like dreadful, much better, you know, that will weigh heavily. Although I can't jump someone from like, you know, here to here based on that. But suppose someone is very close to a boundary, certainly I'll take that into account. Like I say, last term, I didn't give, I think I only gave 1 D. All these people actually didn't exist or had dropped, and I didn't really have anything like this. I had a distribution about down to here in the final score. But, you know, I do want you to worry. If you're down in here, I want you to worry. Okay, I hope you don't worry too much. I want you to worry in a good way where you start, you know, you work hard, make sure you get the homework done. Anyone who just walked in and wants to see their grade, come see me after class, okay? And I'm trying to figure out an automatic way to generate an email but I didn't quite figure it out. And I wasted all my time trying to do that, so I gave up. Any questions? And this is not quite the mix of final, right? I mean, I didn't quite know what to do to reflect the final thing. The final thing, the exams are worth more than the homework. This overdoes the homework. On the other hand, each exam is only 15%. So, I mean, I can't do, you know, but it's somehow, all right. All right, so today I hope we can finish up on StatMech. So we were calculating the density. We're trying to figure out the photon. Well, as I mentioned at the beginning of class, it's the blackbody spectrum. It's the statistical just thing you expect for photons if you have some quantum mechanical system where we don't even, I mean, it is amazing, this analysis. I haven't even said anything about what is emitting the photons or anything. I'm just saying there's photons that have a temperature T, so there's a whole sea of photons. And I said, and I didn't really, I mean, I said, well, I explained that the right answer comes from assigning the photons the particle in a box boundary conditions. Let me be a little more specific in that this will happen in the x dimension, the y dimension, and the z dimension. And I'm going to make L the same in all dimensions, okay? So if that's true, then M x equals 2 over lambda xl equals, let's see, this is, it's 2, if this was 2 pi over lambda, that would be k. So this is kx over pi. Or let me read, sorry, we're going to write just a tad different. A pi over L kx. Can you guys read that over there? Very straightforward. All right? Then what am I going to do with that? So I said, so I'm trying to get the density of states, trying to get D of E. All right, this is sort of the number of photons. Well, I'm not going to write it down again. D of E dE, right, is the number of photons. Well, I'm going to write it down again because there's no other way to describe it. It's the number of photons in this case with E between E and E plus dE. Okay, so I wrote down a condition for a number M, which is running 0, not 0, but 1, 2, 3, 4, 5, whatever, and K. Now for a photon, isn't it the case E equals PC, all right? And P for quantum mechanics is h bar k c. So K is E over h bar c, right? Okay. And so now I'm kind of relating energy to K. Well, no, I am relating energy to K, and then I can relate it to this number M. I got to do a little bit more work, right? K is a vector in three-dimensional space. All right, and when I write this that just E equals h bar k, that's kind of a scalar equation. I really need, I really need to say k squared, which is, the magnitude of the vector squared. That's equal to, well, actually, sorry, I don't want to, that is right, but I want to do it a little differently. I want to think of k there, but I also, in each dimension, x, y, and z, I can think of having a vector m, okay? Because I've got mx, my, mz. This is sort of more mathematical. K has some real quantity. M is just these numbers that are counting the, how many wiggles are in the box. But I should say that m squared is mx squared plus my squared plus mz squared. But if I add up mx plus mi plus mz, by God, isn't that, that's going to be pi squared over L squared, kx squared plus ky squared plus kz squared. So that's just pi squared over L squared E squared is m squared. No, not k squared, sorry. K squared, just k squared, where k is, as I wrote, k is k vector magnitude. Okay? And then I can relate k and e there. K is e over h bar c, so this is pi squared over h bar squared, c squared, L squared, E squared. All right? Okay, so now I've related this number m, which is thought of as like if I make a vector out of these three numbers, which are the number of modes in the three dimensions, that's just straight algebra to get to here. That's straightforward, it's just algebra. And combining terms. Now here's a slightly subtle argument. If I think of m as being large and sort of being a continuous quantity, okay? This question about how many photons are between some energy and the energy plus dE turns into a question about how many photons with m between some value m and m plus dm. Right? I mean, I've got a lot of little numbers m. They're integers, I count them. And this is relating a vector I make out of those mx, my, and mz's, and it's relating it to energy. So I ought to ask how many photons there are in some range of m here, and m means now the vector magnitude. And that's, what that is in a space of mx, my, mz with a vector m, that's, m is all the m's are greater than 0. They're, right? So what that is, if I'm thinking about having a vector with a length m and a thickness dm, this is just a shell. And the volume of the shell, well, if it was a full surface, it'd be 4 pi m squared dm, right? That's like the volume in a shell in m space. But I'm only talking about m greater than 0. All right? And given that, so that this number of photons is between m and m plus dm, that is the number, that's equal to pi over 2 m squared dm. And what I could do is just say that's dm de dE. Okay? Then, and m is a function of energy here. All of this is equal to the number of photons between E and E plus dE. I'm just very simply making a transition from talking about M to talking about E. And therefore, this density of states, it's if I can write down the total number as something times dE, the density of states is just the prefactor of dE. So the density of states is pi over 2 m squared dm dE. Okay? And so this is pretty straightforward. There's m squared. It's also true if I just take the square root of this equation that m is pi over h bar c l e, and therefore dm is pi over h bar c l. Okay, so dm times m squared, plug it in, pi over 2. M squared was pi squared pi over h bar c l cubed. I'll get one factor of that prefactor from m squared and one factor from dm. E squared, and then that's dm is this dE. dm dE is just the pi over h bar cl. Okay? Ah! I made some simple error going right here. M is pi L over K, pi over LK. So what did I do wrong? Oh. I went too fast. This is L over K. This is L over pi K. I am very sorry. It's plowing on and on. Right, this is straightforward. Gosh, so straightforward, I messed it up. Let's do it again. 2 lambda over L is 2 pi over pi, that's 2, over lambda L, and that's K. So it's L over K, L over pi K. So this was just upside down. Yeah.
I can't read that too well from over here. Does it say 1 over pi, 2 pi over lambda L?
1 over pi, 2 pi over lambda times L.
Wouldn't that simplify to 2 over lambda times L?
It started out as 2 over lambda times L.
2 times L over lambda.
2 times L over lambda, sorry. But I wanted it in terms of L, and I wanted it in terms of K. All I was doing is changing lambda to K. Because K is 2 pi over lambda. Or that's the basic definition of K. This was a very straightforward plug-in. Sorry I messed it up. Okay? I'm just changing from lambda to K. That's all I'm doing. Okay, so there's the density of states. That's not quite right. There's one small tweak to it. There's actually 2 spin modes for a photon. This is sort of an advanced topic. Remember a photon I said was spin 1? So it ought to have ml equals 1, ml equals 0, and ml equals minus 1. It turns out that a photon is a special particle. And I don't have time to explain this, but in fact, it only can be spin 1 or spin minus 1. The spin 0 doesn't work for a massless particle. That's a bit subtle. So finally, I just need to multiply this. I need to multiply this by 2. And so it's L squared, it's L cubed. The 2's gone, pi squared, h bar cubed, c cubed, e squared. And also, what is L cubed? As I mentioned last time, I introduced this box, which seemed kind of arbitrary, and it's got a length L. Now, I said L was the same in all 3 dimensions. So L cubed is a volume. Okay? And that's what the density of states is. And we can calculate it. You know, and then the fact is, so, just to, I mean, okay, I hope you can just follow the math. And to explain what we're doing, by putting the particles in a box, by putting this boundary condition on them, I go from a case where, I mean, you might have said, look, I mean, why don't I have just an infinite number of photons at any possible energy? I mean, why not? Okay? There would be sort of no way statistically to count them, but why not have an infinite set of possibilities? And it turns out all quantum mechanical particles need to be thought about this way. This maybe seems a little dry and abstract, but I gave you this calculation. We went through it. I mean, it's in the book. But the point is that this is really what happens. And all quantum mechanical particles do this. They behave as if they're in a box. They have certain wavelengths which are allowed. That gives you a way of calculating how many states there are to give an energy range. And it goes like energy squared, which isn't surprising. That's just the result of the notion, and this is an important notion, was a tad subtle, that if you're counting these numbers m, you're basically talking about a shell. And a shell has a surface area which is proportional to m squared, which is proportional to energy squared. And at the end, that L which we introduced, which I said was kind of artificial, turns into the volume. And this is a density of states including a volume. And then often what you would do is you'd say, oh, I don't really mean that. I want a density of states per unit volume. And you just divide V out. And so then it's just gone. How many photons in some arbitrary, what's the density, the physical density per unit volume of photons in a radiation field that's given by a temperature, the V goes away and I just have this result. But I could only get it by first sticking them in the box, but then the box at the end just goes away. Okay? And this is what I wanted. I wanted the density of states. I needed it, right? Because as a reminder, to calculate anything now, the basic prescription is I multiply density of states by a number of particles that has that state given the energy. That's this occupation number that we calculated last time for a photon. Okay? So finally, not just the number, this is misstated a little bit. This is how many photon modes, if you will. Just considering this quantization condition, the number of photons between E and E plus dE, including the temperature dependence, was this N of E, which we calculated last time, times the density of states. And just to write the two numbers down, this was this term e to the minus, no, actually there's a plus E over KT minus 1 times that beast. And also, let's do this per volume. Okay, so I'm going to divide the volume away when I multiply by the density of states. So I simply have a prefactor, which is pi squared h bar cubed c cubed. And then I have e squared. All right? And that's a famous formula. That's a famous formula. It's not that you should memorize it, but I want you to know where it came from. This BIP was this really kind of interesting, tricky mathematical calculation using the Boltzmann distribution and the fact that I can count all sorts of, I can have any number of photons in a mode, 0 or 1 or 2 or 3 or 4. Remember, and I did this trick with the exponential series, infinite series of exponentials. And then the other parts come from saying, okay, fine, I have a mode. How many modes are there? And that was this density of states argument. So there's these two pieces to it. I said that the beginning of quantum mechanics, one of the beginnings of quantum mechanics was that people predicted the energy in a black body. And why we call this a black body? We call it a black body because if something is completely black, it absorbs all radiation, it also emits all radiation. I've talked about that before. And if it does that, then it will be in thermal equilibrium. Like if the table has a certain temperature and the whole room has a certain temperature and everything in the room is painted completely black, it'll be emitting all possible photons it can and absorbing all photons it can, and there will be a photon field in this room that's in equilibrium with the rest of the walls of the room. Okay? So this is going to apply to the photons when they're in contact with the material that's black and everything's in thermal equilibrium. So we call this a black body spectrum. And I mentioned that there was a classical result which fell apart. The classical result was Boltzmann had figured out these exponential factors. He hadn't thought about quantum mechanics. He didn't have the right counting statistics, so he didn't have 1 over e minus 1. He just had the e to the energy over kT. That as a probability. But actually, that's not much different, because if e is big, this term this dwarfs that, and this just becomes that. What he didn't have is was a detail. He didn't have this quantize the particles in the box notion. Or Boltzmann, when he first calculated all of this, and when people first applied it to light, they didn't have that concept. They didn't get the density of states. They didn't get the energy squared piece, therefore. And therefore, they didn't know that they didn't have a way of understanding why, with the real measurement, the energy, as you go to low energy, the spectrum falls off and drops to 0, which it does. Okay? Okay. What else do I want to say about this? Often, instead of talking this way, we use energy was, it's h bar omega for a photon. It's also, which is consistent with the other energy formula we wrote. But it's also hf, okay? Where h is the Planck's constant not divided by 2 pi. Of course, h bar is Planck's constant divided by 2 pi. And f is just the pure frequency. And that's useful when we talk about visible light. If I transition over and I plug in, what I really need to do if I'm going to do that, I'm sorry, the number of photon modes here. I have to write dE to get the number of modes. If I want to write the total number, without the dE, it's not a proper number yet. So if I have this, and of course then therefore I have dE equals HDF, and I plug those in, this whole thing becomes, let me see, I have h squared, f squared, h df. So I have h cubed, I have h bar cubed, and so the h's cancel, and this is 1 over 2 pi cubed. So it's 8 pi cubed in the numerator, and there's a pi squared there. So I have 8 pi over c cubed e to the hf over kt minus 1 f squared df. Not too important, but that just, I wanted to rewrite it. And that's plotting it in frequency as a function of frequency. And let me just sketch it. It's in the book, but you just need to see it. Because it really is one of the beautiful results in physics, this blackbody spectrum. I mean, what's amazing is that you calculate all this, and this was a fairly abstract calculation. And you know, that's what you go out and you measure in the world. I think I showed you a curve in the first class that the sun has a spectrum of light which really looks very much like this calculation. This piece here is that, is that, and this piece here is that. Okay? And this vertical axis, if I had to give, there's a nomenclature problem. The book doesn't like to use a little n for this, but I would have called it little n. Maybe they did, I can't remember. Anyway, it looks like that. Just for your information, I want to explain one more thing. If this is at one temperature, well, suppose this is, I don't know, well, just to use numbers that were in the book, this is 4,600 Kelvin. Then you get, this is, well, it's 0.5 gigahertz, no, terahertz, times 10 to the 15th hertz. For a wavelength, and that's what's a little more interesting, this is 630 nanometers. I don't know if you know your light colors, but that's red. That's pretty red. If I take a lower temperature, a much lower temperature, the overall amplitude gets down and it gets shifted to lower frequencies. And so it turns out that if you ask what's the peak wavelength in that distribution, that's a pretty simple min-max problem, right? Just take the derivative of this with respect to frequency, set it equal to 0. It turns out that when you do that, this is what happens. Lambda max times t is a constant. And this is worth knowing. It's 2898 microns Kelvin. I mean, clearly you don't want to, well, you might memorize that. Actually, I would always wanted to memorize that, but I always forget it. But you should memorize, I think, the fact that lambda times t is a constant. This is an important thing to know. All right? What's the temperature of the sun? Well, gee, do you know that, I'm not microns, micrometers, microns times Kelvin. Micro K. Microns, right? Visible, yellow light, sun's yellow, is around 5,600 0.56 microns. So if I say t, that's about half. So divide by lambda max, which is about half a micron, that's 3,000. I'd say about 6,000. It turns out the temperature of the sun is 5,800 Kelvin. It's just from that. Room temperature, you guys, what are you doing? Lambda student equals 3,000 divided, you're at 300 Kelvin. It's 10 microns. Okay, so you're emitting photons that are 10 microns in size. That's infrared. And you remember the photos I showed you of that. Now, I said I would calculate just something about global warming. Let's do that real quick. What's the temperature? Oh, heck, I'll do it here. Because there's one other just solid result you should know about blackbody spectra. Let me write it in that form. No, not in that form. Let me ask, what's the average energy of a photon given what I've just learned? And what it is, and you need to know how to do this, right? It's the energy. I'm taking an average of something, so I write the thing, and then I have to do, sorry, I want to do it this way. And then I've got to multiply it by probability and average. And again, this had the okay, this term. And but in the units I just had, it was 1 over pi squared h bar cubed c cubed e squared dE. Okay. I'm going to do a simple dimensional analysis of this. I'm going to use an argument which we use a lot in physics because I don't want to do any hard work here, but I want the answer. Okay, this is proportional to the integral of e cubed dE because I had the e squared and now I'm averaging on the e function. That looks like a kind of nasty integral, e squared over this 1 over an exponential minus 1. All right? And I don't want to do it. So what I'm just going to say is, well, there isn't, what's key is the temperature bit. Okay? Oh, and I'm going from 0 to infinity. Those are the allowed energies, 0 to infinity. So I'm going to say U is energy over kT, and therefore du equals dE over kT. So where I see E, I'm going to write U kT, and where I see dE, I'm going to write du kT. And this integral becomes proportional. I'm going to drop a term in terms of k. Well, oh no, actually I'll write it directly. That's kT to the 4th, integral 0 to infinity. If E is infinity, U is still infinity. U cubed du over e to the u minus 1. And let me erase all my other stuff here so you can see that clearly. All right? This is just some number. You can look it up. I don't really much care what it is. So the point is this is proportional to T4th. That's a key result. The energy, the average energy emitted by a black body goes like the 4th power of the temperature. We actually had we had a meltdown in my lab 2 weeks ago. We had a piece that we had spent a few $1,000s buying, machining, designing. It took us about a month. And we wanted to warm it up to drive water out of it. It was made of Teflon or polyethylene. And we put it in a big oven that we warmed up to well below the melting temperature of polyethylene. And we did a test piece and it worked fine. And we put this other piece in and we baked it for a week and we used a mass spectrometer to look at the gases coming out of it and everything was great. And then we stopped and we let it cool down. It was just in this big tank. The piece was about yay big, piece of plastic. We opened up the tank and the piece was melted. The reason it was, well, we were pretty bummed. The reason it was that there was, we'd changed the way we put a heater on this outside of this big metal tank and one spot got really, really hot. And it emitted a lot. That one spot got about twice as hot as everywhere else. We had a bunch of thermometers. We were monitoring. We weren't anywhere near the melting temperature of the plastic. But that one spot was probably literally twice as hot. Well, this is out. By the way, if you do these things, you have to use Kelvin, right? Where 0 is 0 and high temperature is real high. And that one, maybe it wasn't twice as high, but it was quite a bit hotter. The energy emitted by that one spot totally dominated. And then it turns out, we found out after the fact that polyethylene has a strong absorption band for infrared light that's higher in wavelength, higher in frequency than the normal infrared light. And so that one spot got really hot, emitted a bunch of light in a black body sense, and the blackest thing in our chamber in that waveband was the piece of plastic. And so we just cooked it. The whole rest of the chamber was a moderate temperature that was all monitored and it was okay. The black body radiation dominated, and it goes like temperature to the fourth. So it's a really strong function of temperature. The power emitted is not the energy, but if you may have learned this already in E&M, or you know, it's not a surprise that the power emitted is directly proportional to the energy. There's just a factor of C in there. Yeah?
You go through that whole thing, is that how you derive the Stephon Boltzmann law?
That is the Stefan Boltzmann Law.
Well, I mean, without the proportionality.
Yeah, no, if I hadn't drawn, okay. That was the energy.
Yeah.
I didn't do the power. The power is directly related to the energy with a factor of C in it, I believe. Okay? And if I just hadn't dropped the factors because I got tired of running around with them.
Yeah.
But I mean, I was exact at this point. Yeah. In fact, the Stefan Boltzmann law is that the power, I'm going to put back in the factors. I've got to translate from an energy density to a power and just take my word for it. It's written this way. This is a famous result. That's the power emitted by a black body. This is the emissivity. Okay? This is a constant that was this bit plus another factor of C to change it from energy to power. Okay? And I didn't, here I just considered, it's a little more than that, but nothing, I've done 98% of the hard work, okay? This is a density in the photons, but if I want to talk instead about a surface that emits, I have to think a little bit and turn it back into an emitted power per unit area for a surface. And that's what the Stefan Boltzmann law does. So I have to multiply by, this is the area of the surface. This is the so-called Stefan Boltzmann constant. It's 50 milliwatts per centimeter squared at room temperature. Anyway, and that's T4th. Anyway, so that's a famous result. And there's this, remember I went through this before. Why did I put the emissivity? Well, no, it is the emissivity, but also the absorption is exactly proportional to emissivity because you either absorb or you reflect. And in equilibrium, if you're absorbing, you also have to be emitting at the same amount. All right. Actually, this is what I wanted. I'm not going to finish StatMech quite today, but I will do one thing. Let's calculate the temperature of the Earth. Let me just do it real quick. Okay, so how do we calculate the temperature of the Earth? Here's the sun. It has a radius. R, that's the symbol for solar that astronomers use. There's some distance L to the Earth. I think there's a symbol for the Earth, but I'm not an astronomer. I don't know it, so I'm going to call it RE. Okay? And that's the picture. And the sun is emitting black body radiation. And the Earth is absorbing it. The power absorbed, let me write it this way, the power absorbed at the Earth, that's on the Earth, it's absorbed, is what? This is the power in a radiation field. And I have to think a second. All the power at the sun, the total power at the sun, is going to be epsilon sun, which is 1. I remember I showed you the spectrum. The sun has really a very high emissivity. It's basically, it follows that curve exactly. This emissivity is either 1, in which case you get exactly sigma A t to the 4th. Well, this is the Stefan Boltzmann constant. Or it can be less than 1. So for the sun, it's 1. Sigma A is 4 pi r sun squared times t sun 4th. Okay? That's the power emitted by the sun. And now, if you're some distance L away, what you have is that what happens at the Earth, you have the total power from the sun divided by 4 pi L squared. That's this huge surface that it's gone into. And then the Earth subtends pi r Earth squared. Okay? I don't know if you ever thought about that. If you have a sphere and you say, what's the effective surface of a sphere? It's just the formula for a circle, even though the sphere had the curvature to it. And we could prove that, but just it makes sense, right? However, the Earth has to absorb with the Earth's emissivity in the visible. Remember I said that you absorb proportional to epsilon, proportional to emissivity. That's very simple. That's the amount of energy that the Earth absorbs. How much energy does the Earth emit? And notice I just took one face of the Earth, one side, pi r squared, not 4 pi r squared, all sides of the Earth. The Earth emits some power. And in equilibrium, the amount you absorb is the amount you emit. The Earth is sort of an average temperature. We're rotating so fast that even though it's a little colder at night than in day, let's say it's one temperature, you're emitting in the infrared. It's no longer the same emissivity. Emissivity can be frequency dependent, and it's different. And the emissivity is the thing that depends on like the cloudiness or on greenhouse gases. Okay? Times sigma times A Earth, which is 4 pi R Earth squared, times T Earth fourth. This is a darn simple formula. Okay? This is a darn simple formula. So let me just equate this and this. I didn't write out the power from the sun. The power from the sun was sigma 4 pi r sun squared divided by 4 pi L squared. The 4 pi goes away. There was emissivity, which was 1 for the sun. There's still pi r e squared. How much the Earth absorbs in the visible, how much the Earth emits in the infrared, sigma 4 pi r Earth squared T Earth to the fourth. Sigma cancels out. And there's a pi left over here, which can cancel that pi there. And that's it. That's as simple as I can get. And I'm seconds from being done here. T Earth. Huh? And the radius of the Earth cancels out. Thank you. So the temperature of the Earth is R sun over L. Let me see, this was fourth and those were squared. So I'm talking about the square root of them. Oh, and I forgot the biggest term here of all, T sun to the fourth. It was certainly there in the power of the sun. So I take the fourth root and T sun comes straight out. I haven't arranged myself on the board quite right. T Earth, let me scoot it over a tad, equals epsilon visible over 4 epsilon infrared, all to the quarter power. I invite you to plug in. Our sun is, I have the numbers here, I'll read them out. Our sun is 6.9 times 10 to the 8th meters, 69 million meters. Distance sun to Earth, 1.4 times 10 to the 11th meters. Let's pick, and let's take epsilon visible equal to 1. Let's take epsilon infrared equal to 1. Then I'm out of chalk, come on. Then we calculate T Earth is 279 Kelvin. That's about right. If I take instead, here's what's global warming. Here's the scary part. If this denominator goes down, epsilon infrared, because we put a gas in I mean, realize that, you know, the Earth because the light's coming in at a high frequency, visible, and the Earth is emitting is 10 micron infrared, these emissivities are not the same. And specific materials like our unfortunate plastic in our chamber that melted because it had an absorption band in the infrared, they have they can be far from a black body due to the details of the surface that doesn't want to just act like this sort of ideal black body. And the greenhouse gases are such that they drop this, okay? And if I pick a smaller number, 0.5, then T Earth goes to 323 Kelvin. Bad news. That's pretty hot. Okay? So the physics behind it is really straightforward. What is not at all straightforward is what the epsilons are. Whoa, that's totally complicated. If I have a lot of clouds, epsilon visible is not 1. Light's being reflected off, etc. Okay? So it's a complicated story. All right? But that's the basic idea. The calculation is this simple. And we'll stop there.